Welcome to The Explainer. Today we're getting into the nuts and bolts, well, more like the teeth and cogs of the hidden world that makes pretty much everything work. We are talking about mechanical gears, the real unsung heroes of engineering that are quietly turning power into motion all around us every single day. Okay, let's just dive right in. Now, at first glance, this diagram, yeah, it might look a little intense. You've got all these curves and angles and a ton of labels, but I want you to think of it like a puzzle. Because by the end of this, I promise, you're not only going to understand what all these little parts do, but you'll see the simple, kind of beautiful principles hiding in plain sight. All right, so to start things off, let's establish exactly what we're talking about here. What is the one fundamental purpose of a gear in our mechanical world? At its heart, a gear is a really simple idea. It's basically a wheel with teeth. And its whole job is to transmit power and motion when its teeth mesh with another gear. It's this beautiful, interlocking dance that lets power flow from one part of a machine to another. So why even use gears? Why not just connect things directly? Well, because gears are absolute masters of transformation. They take an input speed and an input rotational force, which we call torque, and they change them. And that right there is the whole point. If you need to make something spin faster or slower or with a lot more force, a gear is almost always the answer. So how do they actually do it? How do they pull off this little bit of mechanical magic? Well, it all comes down to one absolutely critical concept, the gear ratio. This, my friends, is the secret sauce. And the best part is, the gear ratio isn't some super complex formula you have to memorize. It's literally just a comparison. The number of teeth on the gear that's doing the driving versus the number of teeth on the gear that's being driven. That's it. That simple count dictates everything that happens next. And this slide just illustrates that trade-off perfectly. Check out the left side. When a small gear with fewer teeth drives a big gear with lots of teeth, that big gear turns much slower, but it does so with more force, more torque. Now, look at the right. When a big gear drives a small one, that little gear spins like crazy, way faster, but with less force. It's a perfect inverse relationship, and it's how engineers get the exact performance they need out of a machine. Here is a perfect real-world example. A 3-to-1 ratio just means that for every 3 times that little 10-tooth gear spins all the way around, the big 30-tooth gear only manages to complete one single rotation. So you get a 3 times speed reduction, but in return, you get a 3-fold increase in torque. Simple, powerful, and honestly, pretty elegant. Now, making 2 gears mesh perfectly isn't as simple as just, carving some triangles onto a wheel. No. Each and every tooth is a tiny masterpiece of precision engineering, designed to roll against its partner flawlessly, without any slipping. So remember our little puzzle from the beginning? Let's decode some of it. This diagram shows us that every single curve has a name and a very specific job. That pitch circle? It's the imaginary line where the 2 gears really touch and transfer power. The addendum is the height of the tooth above that circle, and the dentum is the depth below it. All of these dimensions have to be absolutely perfect for a smooth ride. So engineers use a few key ingredients to design these perfect teeth. First is the module, which is kind of like a universal measurement for the size of a tooth. And here's the deal. For 2 gears to mesh, they must have the same module. Then there's the number of teeth, which, as we know, sets that all-important gear ratio. And finally, the pressure angle, which is the exact angle that force is transferred from one tooth to the next. And that pressure angle, it is incredibly important. And it turns out there's a bit of a magic number. So why is 20 degrees so common? Well, it's pretty much the sweet spot. An angle of 20 degrees makes the base of the tooth wider and stronger, and it seriously reduces the risk of the tips of the teeth accidentally bumping into the bottom of the gear groove, which is a big problem called interference. Okay, this table might look like just a wall of numbers, but don't worry about the specific values. The point here is to see the incredible precision involved. You start with a set value, like the module and the number of teeth you want, and every other dimension, from the overall diameter right down to the base circle, is meticulously calculated to thousandths of a millimeter, all for a perfect, efficient fit. All right, so now that we've got the basic principles down, let's have some fun and look at the wider family of gears, because you'll see there isn't just one type. There's a specialized gear for almost every single job you can imagine. So on the left, you've got the classic, the most common type, the spur gear. Its teeth are straight up and down, parallel to the shaft. Simple, super effective, but they can be a bit noisy because the teeth engage all at once with a clack. Now on the right, you have the helical gear. Just by angling the teeth, the engagement becomes gradual and smooth. They run so much quieter, which is exactly why they're used in things like car transmissions. But what happens if your shafts aren't parallel? What if you need to turn a corner? For that, you need bevel gears. They're shaped like cones, so they can transmit power around a 90-degree angle. And for those times you need a massive speed reduction and a huge boost in torque, you bring out the worm gear. The worm, which looks like a screw, can easily drive the gear. But here's the cool part. The gear often can't drive the worm. It's self-locking, which is incredibly useful for things like elevators and hoists. And the versatility just doesn't stop. A rack and pinion system literally unwraps a gear into a straight, flat bar. This is how you turn a spinning motion into a back and forth linear motion. Think about your car's steering system. And then you have internal gears, which put the teeth on the inside of a ring, allowing for these incredibly compact and powerful planetary gear systems, where one gear fits right inside another. So, we've gone from the really basic concept of a gear all the way to this complex family of specialized designs. Let's bring it all together now and see how all these abstract calculations become a physical reality that does real, heavy-duty work. You see, every single one of these gears, born from those super precise mathematical tables, doesn't work alone. It becomes a vital building block in a much larger system, like the industrial gearbox you see here. They all work together to create these incredibly complex and powerful machines. And here's the crucial takeaway. All of that theory, all those design parameters and different gear types, they all combine to achieve a very specific engineered goal. In the gearbox design in that study, the final total speed reduction was 2.57 to 1. Not 2.5, not 2.6, exactly 2.57. A precise, calculated outcome, all achieved by combining the principles we just talked about. And in the end, that really is the magic of a gear, isn't it? It's the point where abstract math becomes tangible, powerful motion. It's a fantastic reminder that our world is built on all these principles that are so often invisible, but they are always at work. Which kind of makes you wonder, what other invisible engineering is powering your world right now?